Good morning. Welcome to the session for Masters of Business Administration. We will be continuing with transportation and assignment problem. In our last session, we have introduction and some problems related to transportation problem. Today, we will start with assignment problem. Assignment problem is a special case of transportation problem. Here, the number of sources are equal to number of destinations. Rather, we can say that M is equal to N. The objective is to assign the given jobs to the most appropriate machine or person so that the objective function of minimizing the cost or time is achieved. What are the areas of operation? Company wants to transfer M cargo trucks from N different cities, where M is equal to N, so as to minimize the total distance traveled, which will minimize the total cost. In manufacturing processes, the allocation of machines and manpower to minimize the total production cost. Thirdly, we can say that in assigning police vehicles to patrolling area. Next, we can say that in assigning teachers to classes. In assigning contracts to builders by systematic bid evaluation. In assigning sales, marketing people to sales territories. In assigning accountants to account of the clients. Now, what is the difference between assignment and transportation problem? Assignment problem, as we said, is a special case of transportation problem under the condition that the number of sources are equal to number of destinations, that is M is equal to N. There are N factorial possible arrangements. The simplest way of finding an optimum assignment is to write all the N factorial possible arrangements, evaluate their total cost, and select the assignment with minimum cost. But this method leads to calculation problem of forwardable size even when the value of N is moderate. We take our example of if N is equal to 10, the possible number of arrangements is 32,68,800. So it's very tedious job. What is the difference between transportation and assignment problem? If we talk about assignment problem, it is done under the condition that the number of sources are equal to number of destinations. The cost matrix should be a square matrix. And the problem is unbalanced if the cost matrix is not a square matrix. And on the other side, for transportation problem, number of sources and number of destinations need not be equal. The cost matrix is not necessarily a square matrix. And the third one is the problem is unbalanced if the total supply and total demand are not equal. What is the mathematical formulation of assignment problem? As we said, will be a square matrix. So let Xij be the assignments of ith resources to jth activity, such that Xij is equal to 1 if the source 1 is assigned to activity j, otherwise 0. The mathematical formulation is to minimize z is equal to summation I tends to I starting from 1 to n and j starting from 1 to n, and it is a product of Cij and Xij, subject to the constraints that Xij will be equal to 1 and Xij for j equal to n will be equal to 1, and Xij is for all 1 starting from 1 to 3 till n, and j also starting from 1 to 3 till n, where Cij is the cost associated with each point. The most common method which is used in assignment problem is Hungarian method, where the objective function is that of minimization time. Step one, first of all, we will be going for the different steps which will be followed while solving of the problem. And later on, we will see to the problem. Step one, from the given problem, find out the cost table. Note that if the number of origins is not equal to number of destinations, then a dummy origin or destination must be added. Step 2. In each row of the table, find out the smallest cost element. Subtract this smallest cost element from each element in that row so that there will be at least one zero in each row of the new table. This new table is known as first reduced cost table. Next step is to determine an assignment as follows. For each row or column with a single zero element cell that has not been assigned or eliminated, box that zero element as an assigned cell. For every zero that becomes assigned, cross out other zeros in the same row and for the column. And if a row and for a column there are two or more zeros and one can't be chosen by inspection, choose the assigned zero cell arbitrarily. The above procedure may be repeated until every zero element cell is either assigned, boxed, or crossed out. The next step is an optimum assignment is found if the number of assigned cells is equal to number of rows and columns. In case we had chosen a zero cell arbitrarily, there may be an alternate optimum. If no optimum solution is found, that is, some rows or columns are without an assignment, then go to step 6. Draw a set of lines equal to number of assignments which has been made in step 4, covering all the zeros in the following manner. Mark a tick sign to those rows where no assignment has been made. Examine the checked tick marks. If any zero element occurs in those rows, check tick sign the respective columns that contain those zeros. Examine the checked tick columns. If any assigned zero element occurs in those columns, check the respective row that contains those assigned zeros. The process may be repeated until now more row or columns can be checked. Draw lines through all unchecked rows and through all checked columns. Next step is examine those elements that are not covered by lines. Choose the smallest of these elements and subtract the smallest from all the elements that do not have a line through them. Add this smallest element to every element that lies at the intersection of the two lines. Then the resulting matrix is a new revised cost table. There are some remarks for that. To solve an assignment problem in which the goal is to maximize the objective function, multiply the profits matrix through by -1 and solve the problem as a minimization problem. Number 2, if the number of rows and columns in the cost matrix are unequal, the assignment problem is unbalanced. Any assignment problem should be balanced by the addition of one or more dummy points before it is solved by the Hungarian method. Now we will have a look at a problem. How should the task be allotted to a man so as to minimize the total man hours? This is the problem. E, F, G, H are the men and task are A, B, C, D. How we will solve? Here the task and manpower are equal. That means there are 4 men and 4 tasks. They are equal. So straight away we go to step 3. Subtract the smallest element from each row firstly. The smallest element in this is in row is 11. We will be subtracting 11 from all. Secondly, in the smallest element is 13, and in the third row, the smallest element is 15, and in the fourth row, the smallest element is 10. Once this process is completed, then we move to the column. In the first column, the smallest element is 0. In the second, it is 4. In third, it is 1. And in the fourth column, it is 0. We will be subtracting now, column wise, the smallest element from each column. We get this matrix. Now, what to do? We will assign square for those zeros in a row. It will be 0 over there at the right corner. First corner, second row, left corner. We will be leaving this 0 by cross. Third one, third row, we are having 2 zeros. We will be allocating the first one because in the fourth we have already marked. Now in the fourth row, we have already used that 0 in the column, so we cannot move further. Here, in column 3 and 4 does not have any assignment. Row 4 does not have any assignment, so we mark this as tick. Now, this is the condition. Minimum number of lines drawn are 3, which is less than the order of matrix because there are 4 by, this is a 4 by 4 matrix. Which means we have 4 men and 4 tasks. We have assigned only 3 assignments. That means we can say that this is not the optimal solution. Then what? How to proceed? To increase the number of lines drawn to 4, we have to modify the matrix because we have to assign 4. The smallest number not covered by the lines here is 5. We will subtract 5 from the remaining uncovered elements and adding 5 to the intersecting points of the line. So we can see over here in the column 3, 5 will be subtracted. And 5 will be added to all intersecting lines. So we will be adding 13 plus 5, that will be 18, and 0 plus 5, that will be 5, and we will be subtracting 5 from the third column. Now this is the matrix which is obtained. Now, how to proceed further? Again, the assignments are here. First row, second row, third row, fourth row. So we find that now every row and every column has an assignment with it. That means we can say that this is the feasible solution to the problem. Now, your resultant matrix is in the right side. That means the assignment is A to G, B to E, C to F, and T to H. So we will be assigning these values 17 plus 13 plus 19 plus 10. That is equal to 50 man-hours. So this is basically the right procedure of solving the problem. Now, here, again, a problem is given to us. There are 5 different cities and 5 surplus cities. We have to find an optimum assignment schedule. 5 different cities and 5 surplus, that means we can say that this is the balance condition. Now, we will be subtracting the smallest element from each row. We will get the smallest element is in each row is first row is 65, In second, it is 66. And in the third one, it is 57. In the fourth one, it is 60. And in the fifth one, it is 56. So we will be getting this matrix. Now, we will be assigning zeros to the columns, to the rows first. In first row, we have two zeros. We will be leaving over there. We will be continuing with B. We have one single zero assigned. In column, in row 3, we have again 2. In D, we are having 1. And in E, we are having 3 zeros. Randomly, we will be assigning these values. Now we can see that step 5, minimum number of lines drawn having all the zeros covered. We get 4 here, which is less than the order of the matrix because we are having this order is of 5. Hence, the current location is not optimal. Mark, take mark on the row D as it has no assignment. Column C, since row D has 0 in it. Mark, tick row B, since column C has assignment in row B. So we get 3 lines over here. Here, the number of lines drawn having all the zeros covered, we get 4, which is less than the 5. Hence, this is not the current optimal solution. Again, mark tick to row D as it has no assignment. Mark tick to column C since row D has 0 in it, and mark tick row B since column C has assignment in the column row B. To increase the number of lines drawn to 4, we have to modify the matrix. The smallest number not covered by the lines here is 2. So we will subtract 2 from the remaining uncovered elements and adding 2 at the intersecting point of the line. So when we will be subtracting 2 from the row, it will be 0, 0, 0, 2, 4. And it will be for column row A, it will be 2, 0, 0, 2, 2, 0. This will be this. The matrix now has been transformed to minimum number of lines having all the zeros covered, we get 4 here, which is again less than the order of 5. This is not the optimum solution. Now, what is the smallest number? It is 1. The smallest number not covered by the lines here is 1. We will subtract 1 from the remaining uncovered elements and adding 1 at the intersecting point of the lines. So we will get this matrix. Here we can see that we have 5 assignments assigned individually at every row and every column. To increase the number of lines to 4, we have to modify again the matrix. The smallest number not covered by lines is 1. We subtract 1 from the remaining uncovered elements and adding 1 to the intersecting point of the lines. This comes to the final solution. Again, we have to see that what is the status of zeros in every row and every column. In row A, we have single assigned unit. In B, we have single. In C, it is the B1. In D, it is the A1. And in E, it is the D1. Now, we have one assignment in each row and column, but we have 2 zeros in row C and E. Hence, the arbitrary selection of a cell in any of these 2 rows will give us the alternative solution having the same total distance. Randomly, we will be finding out 2 solutions, that is A to E, B to C, C to D, D to A, and E to D. This is the first part. And the second one is A to E, B to C, C to D, D to A, and E to B. When we are finding out the total minimum distance, in both the cases, we got 399 kilometers. That means we have two options, and the total distance covered will be with minimum, which is 399. A special case in assignment problem. This is a case of maximization. We have to find the notable assignment and maximum sales. This data is given to us. This is related to zones and engineers. We have four zones and we have four engineers. That means this is a balanced condition. But how to start it? Converting maximization problem into minimization problem is the first step. Conversion is done by subtracting the maximum element from each element. We will be subtracting 154, which is the largest maximum element. So this matrix will be converted to this form. Now we subtract the smallest element from each row firstly. That is the procedure. After subtracting, we get this. Then we will be subtracting the smallest element from each column. Now, to increase the number of lines to 4, we have to modify the matrix because we are having two lines, and we have to have minimum of 4. Which is the smallest element? We can see in this problem it is 1. The smallest number not covered by the lines here is 1. We will subtract 1 from the remaining uncovered elements and adding 1 to the intersecting point of the line. We get this matrix. Again, we have to repeat step 3 and 4. So still the number of lines are less than the number of matrix. Number of lines are 3, but we want 4. So we will be repeating it, the step again. The smallest number not covered by the lines here is 2. We will be subtracting 2 from the remaining uncovered elements and adding 2 to the intersecting point of the lines. We get this matrix. Again, we see that we have 3 lines and we should have 4. Again, that step is repeated, which is the smallest number from the uncovered areas, that is 2. So we will be subtracting 2 from the remaining elements and we will be adding 2 to the intersecting points. Now we get this matrix. Now we can see that single assignment is there in each row and in each column, which means that this is the feasible solution. Now, going back to the problem, that is P to D, Q to B, R to A, and S to C. The solution shows that the best engineer is P in given richest zone is D, and the worst engineer is given C zone. And the total maximum sales is, we will be adding all these numbers, 154 plus 72 plus 110 plus 56, which comes out to be 392,000. This is related to a problem of assignment. This is a special case, that is airline crew assignment. XYZ operates 7 days a week. According to the given time schedule, layover of 6 hours is given to the crew between the flights. Determine the optimum flight schedule with minimum layover time away from the home. For any given pairing, the crew will be based at that city that results in smaller layover. This is the condition. Now, for each pair, mention the town where the crew should be based. This is the schedule of flights from Delhi to Kolkata and Kolkata to Delhi. Firstly, what we will do, we will construct the table for layover time between the flights when the crew is based at Delhi. Here, 1 minute is equal to 1 unit. As the mentioned time layover is 6 hours, that means 360 minutes between the flights. That means layover between the flight 1 and 101 will be 24 hours, that is 1440 units. Similar calculations have to be made for other flights. Now, we are talking for the layover period from Delhi to Kolkata. The original time which is given to us for flight 1, 2, and 3 on the left side of the screen, that time has been converted into a layover time. 1 to 102 is 9 a.m. to 10 a.m. That means the next day. So that means 1500 units. Similarly, for 1 to 103, it is 9 a.m. to 3:30 p.m. That is 6 hours 30 minutes. That comes out to be 390 units. Flight 1 to 104, that is 9 a.m. to 8 p.m. 11 hours. That is 660 units. And for 2 to 101, that is the complete rotation. That is 22 hours. That comes out to be 1320 units. And we will be calculating this layover time for all the flights. So the matrix, which is on the left side of the screen, is converted into the layover matrix. Similarly, we will be calculating for Kolkata to Delhi. Now for a layover between the flights when crew is based at Kolkata, 1 minute is 1 unit. As mentioned, layover time is 6 hours, that is 360 minutes between the flights. That means layover between the flights 101 and 1 will be 20 hours, which means 1200 units. That is 11 a.m. to 7 a.m. next day. This is the schedule. We will be calculating the layover time for the second unit. That is from Kolkata to Delhi. For 101 to flight 2, it is 11 a.m. to 1:30, which is given in the basic problem, which comes out to 26 hours 30 minutes, which is equivalent to 1590 units. 101 to 4, it is 11 a.m. to 7:30 p.m., which is 8 hours and 30 minutes, which comes out to be 510 units. Similarly, we will be calculating for all. Now we can see that when the crew is based in Delhi, this is the matrix, and when the crew is based in Kolkata, this is the matrix. Now, the layover is marked with star, which denotes that crew is based at Kolkata. Because we have to take the minimum layover time, as it was mentioned in the problem. We can select comparing these two out of 1440 and 1200. 1200 is the lowest, 1500 and 1140. 1140 is the lowest, 390 and 810. 390 is the lowest. Similarly, you can see over here, the Kolkata based crew has been marked with star. This is the workable table. Now, subtract the smallest value from each row and then subtract the smallest row from each column, what we have done earlier also. After the transformation, this is the final position what we see. What we have to start the working. Again, subtracting the smallest value from the each column. Since the number of lines are not equal to number of columns or rows, therefore this assignment is not feasible. Then we subtract the smallest value 60 from the uncovered cell and add 60 to the intersecting lines. Subtracting 60, so we got this matrix. Here we can see that each row and each column has been assigned an assignment, which means this is the feasible solution. On comparing the layout time with the original table, we get for flight 1 to 3, 103, that is Delhi West, layover time is 390. For flight 2 to 104, that is again from Delhi, it is 540. Flight 3 from 101, it is Delhi 51050. And flight 4 to 102, it is Kolkata West, it is 450. That means when we total up, the total time comes out to be minutes is 2430, which is equivalent to 40 hours 30 minutes. Now, another problem which is related to a company has 3 jobs and 4 machines. Each job can be assigned one and only one machine. The cost of each job is given in the table. Determine the job assignment which will minimize the cost. Proceeding, we see that number of rows and number of columns are not equal. That means we have to add a dummy job which will have zero value in it. This is how the matrix has been transformed. Subtract each row from row with the smallest value and then with the column. Here, column subtraction is not required as the value is 0. As the number of lines are not equal to number of rows or columns, subtract each row with the smallest value 5 and add 5 at the intersecting lines, what we have been doing in our earlier problems. As here again, there are 4 lines in the column part. We will see that the smallest element is 4. We will be subtracting this 4 from each of the remaining elements. We get this matrix. Now the allocation, we see that there are more than 1 zeros in the row. Hence, there will be more than one assignment, but the total cost will remain the same. If we take this combination, so we get A to W, B to X, C to Y, and D to Z. When we will be adding up, we get rupees 50. And on the second case, the second arbitration, that is A to W, B to Y, C to Z, and C to X, and D to Z. Again, we are getting the same total cost. Now, construction company has requested bids for subcontracts on 5 different projects. 5 companies have responded. Their bids are represented by this matrix. Determine the minimum cost assignment of subcontracts of bidders, assuming that each bidder can receive only one contract. Number of rows and number of columns are the same. Here the task and the manpower are equal, so we will straight away go to step number 3. Subtract the smallest element from the each row. And in the second step, we will be subtracting the smallest element from the each column. Then we will mark star, square and cross on both the zeros in the column. We get this matrix. Now we have at least one assignment in each row and column. Hence, this is the feasible solution to the problem. 1 to 5, 2 to 2, 3 to 1, 4 to 3, and 5 to 4. We will be adding up all these costs and we get 1,55,000. Now, moving to goal programming. Here, it is another method of solving the linear programming. The objective of a business organization is to maximize profits and to minimize expenditure, loss, and wastage. However, a company may not always attempt profit maximization. At times, a necessity may arise to pay attention to other objectives also. A manufacturing organization may like to ensure uninterrupted supply of its products, even if it means additional expenditure to the procurement of raw materials or personal delivery of goods during truckers' strike, etc., with the objective of assuring the good will-being of the customers. A company driven by social consciousness may depend a portion or may spend a portion of its profit on the maintenance of trees, parks, public roads, etc., to ensure the safety of the environment, with the objective earning the support of the society. A bank may offer services beyond normal working hours or on holidays, even if it means payment of overtime to the staff, in order to adhere to the policy of the customer satisfaction on priority basis. A business organization may accord priority for the welfare of the employees, and so a major part of the earning may be on the employee welfare needs. The above typical instances go to the show that the top level management of a business organization may embark upon different goals in addition to profit maximization. Such goals may be necessitated by external events or through internal discussions. At times, one such goal may be in conflict with the other one. Goal programming seeks to deal with the process of decision making in a situation of multiple goals set forth by a business organization. A management may accord equal priority to different goals, or sometimes a hierarchy of goals may be prescribed on their importance. One has to strive to achieve the goals in the accordance with the priorities specified by the management. Some of the goals that may be preferred by a business organizations are maximum customer satisfaction, maximum goodwill of the customers, maximum utilization of the machine capacity, maximum reliability of the product, maximum support of the society, maximum utilization of the workforce, maximum welfare of the employees, etc. This list is not ending. Since different goals of an organization are based on different units, the goal programming has a multi-dimensional objective function. This is in contrast with a linear programming problem in which the objective function is unidimensional. The solution of any linear programming model is based on the cardinal value, the number that expresses exact number such as 1, 2, 3, such as profit or cost, whereas a geometric programming model allows ordinal ranking of goals in terms of their contribution or importance to the organization. Since it may not be possible to obtain information about the value or cost of a goal, the specific numerical target value desired to achieve, or a sub-goal, therefore their upper and lower limits are determined. Usually, desired goals are assigned priorities, and then these priorities are ranked in an ordinal sequence. Whenever there are multiple incommensurable, that means different units of measurement, goals, and linear programming model incorporates only one of these goals in the objective function and treat the remaining goals and constraints. Since the optimum solution must satisfy all the constraints, this implies that the several goals within the constraining equations are of equal importance, and these goals have absolute priority over the goal incorporated into the objective function. Distinction among objectives, goals, and constraints. The knowledge of the difference among the terms objective, goals, and constraint is helpful in the formulation of any GB model. A goal is the acceptable or target value to be achieved in terms of performance level, whereas an objective implies optimization. It can be maximization or minimization of the measures of performance in terms of cost or profit. A goal and constraint appears the same in terms of their mathematical formulation. However, for a goal, the right-hand side value of the target level to be achieved. But for constraint, it is desirable to achieve the right-hand side value. Otherwise, it is considered violated, leading to an infeasible solution to the linear programming problem. In a linear programming model, the objective is to optimize the given measure of performance or effectiveness, subject to the set of constraints on the availability of resources. But GP model does not take into consideration the fixed value of available resources and is based on upper and lower targets value to be achieved in terms of their uses. Single goal with multiple sub-goals. An objective goal is the result desired by the decision maker. The goal may be underachieved, fully achieved, or overachieved within the given decision environment. The level of goal achievement depends upon the effective planning with respect to the performance of any activity. Mathematically, one unit of effort applied to activity Xj might contribute an amount Xij towards the ith goal. If the target level of the ith goal is fully achieved, then ith constraint is written as summation of j equal to 1 to n, and it is product of x aij and xj, which is equal to bi. To allow underachievement or overachievement in the target value, that's the goal. Let di minus the negative deviation from the ith goal, that is underachievement, or amount below the target value, and di plus, which is a positive deviation from the ith goal, that is overachievement or amount above the target value. Using these notations, then the goal can be rewritten as summation of j equal to 1 to n, product of aij and xj plus di minus di plus, which is equal to bi, where I is 1 to n. Mathematically, what we can say that it is the summation, it is basically a combination of value of the objective plus amount below the target minus amount above the target, which is equal to the target value, which is the goal. Since both underachievement and overachievement of a goal cannot be achieved simultaneously, one or both of these deviation variables may be zero in the solution. Now, we take up a problem and we will be solving this problem with the goal mechanism. A manufacturing firm produces two types of product, A and B. The unit profit from A is 100 and from B it is 50. The goal of the firm is to earn a total profit of exactly rupees 700 in the next week. Model formulation, how the model formulation will start. To interpret the profit goal in terms of sub-goals, which are sales volume of the product. Let X1 and X2 be the number of units of product A and product B be produced respectively. The single goal or profit maximization will be maximize profit z equal to 100x1 plus 50x2. This is our basic function. Since the goal of the firm is to earn a target profit of rupees 700 per week, the next goal can be restricted to allow for underachievement or overachievement as 100x1 plus 50x2 plus d1 minus d1 plus, which is equal to now 700. Now, the goal probability model can be formulated as minimize z equal to d1 minus d1 plus, subject to the constraints. These are the constraints: 100x1 plus 50x2 plus d1 minus d1 plus equal to 700, and x1, x2, d1 negative and d1 positive will be greater than equal to 0, because these are non-negative constraints. D1 negative is underachievement of the total profit of rupees 700, and D1 positive is the overachievement of the profit goal of rupees 700. If the profit goal is not completely achieved, then the slack in the profit goal will be expressed by a negative deviation, that is D1 negative from the goal. But if the profit is seen in excess of rupees 700, then the surplus in the profit will be expressed by positive deviation variable, that is d1 plus from the goal. And if the profit goal of exactly 700 is achieved, then both d1 plus and d1 minus will be 0. Here the solution will be any linear combination of x1 and x2 between the 2 points x1 equal to 7 and x2 equal to 0, where and x1 is equal to 0 and x2 is equal to 14. This straight line is exactly the iso profit function line when the total profit is rupees 700. What are the different steps which are to be followed in formulating a general goal programming model? The procedure algorithm is to formulate a GP model in summarized below. Identify the goals and constraints based on the availability of the resources or constraints that may restrict achievement of the goals. Second one is determine the priority to be associated with each goal in such a way that goals with priority level P1 are most important, those with priority level P2 are next most important, and so on. Third one is to define the decision variables. Fourth one, formulate the constraints in the same manner as in the linear programming model we had been doing. For each constraint, develop an equation by adding deviational variables, that is d1 negative and d1 positive. These variables indicate the possible deviation below or above the target value. Write the objective function in terms of minimizing a prioritized function of the deviational variables. Now we take another example to understand what we have, how we will be following different steps. A firm produces two products A and B. Each product must be processed through two departments, namely 1 and 2. Department 1 has 30 hours of production capacity per day, and Department 2 has 60 hours. Each unit of product A requires 2 hours in Department 1 and 6 hours in Department 2. And each unit of B requires 3 hours in Department 1 and 4 hours in Department 2. Management has rank ordered the following goals. It would like to achieve in determining the daily product mix. First one is P1, minimize the underachievement of total production of 10 units. P2, minimize the underachievement of producing 7 units of product B. P3, minimize the underachievement of producing 8 units of product A. Now, formulate this problem as a GP model and then solve it by using the graphical method. As starting at the basic principle is to start with the model formulation. So let x1 and x2 be the number of units of product A and B and D1 minus and D1 plus with the underachievement and overachievement associated with goal I. Then the GP model is stated as minimize Z equal to P1 D1 minus plus P2 D2 D3 minus plus P3 D2 minus. Now this is what are the different constraints associated with the problem. First one is 2x1, which is mentioned in the problem. 2x1 plus 3x2 less than equal to 30. 6x1 plus 4x less than equal to 60. Plus the third one is x1 plus x2 plus d1 negative minus d1 plus equal to 10. X1 plus d2 negative minus d2 positive equal to 8. Fifth one is x1 plus d3 negative minus d3 positive equal to 7. And all di x1, x2, di plus di minus, they all will be equal to, but they all will be equal to and greater than equal to 0. The first two constraints, 1 and 2 in the GP model are system constraints, whereas constraint 3 and 4, 3 to 5 are goal constraints. When we will plot this, here in the figure we see that the solution space associated with the two system constraints and the lines associated with goal constraints with deviational variable marked. It may be noted that larger the distance of the point from the goal constraint, the larger the value of the corresponding deviational variables. The closer a point is to goal constraints, the smaller the value of deviational variables associated with the goal. We can see gray marked area which is on the left side of the graphical solution. And all the constraints, all the 5 constraints are written at the top. The first priority goal is to minimize D1 negative, which represents underachievement of joint total production goal of 10 units. Thus, all the possible points that have positive values of D1 negative have to be eliminated as shown in the figure. So this has been removed. The line area represents all combinations of product A and B, thus that can be produced and that satisfy or exceed the production goal of 10 units. The second priority goal is to minimize D3 negative. As shown in the figure, the points eliminated are those that lie above the second goal constraints. These represent combination of product A and B that fall short of the production goal of 7 units of product B. The third priority is to minimize D2 negative, which represents the underachievement of the production goal of 8 units of product A. In the line area ABC, each point involves the underachievement of the third goal. The optimum solution occurs at corners point C, where D3 negative is made as small as possible. At point D or E, they are on the same line. D2 negative, which becomes 0, and it would give positive values for D3 negative, sacrificing a higher priority goal, which is not allowed. Since point C occurs at the intersection of constraint 1 and 4, by solving these equations, we get x1 equal to 4.5 and x2 equal to 7 in the given constraints. We find that Department 1 has utilized its maximum capacity of 30 hours. Department 2 has unused time slack of 5 hours. There is an overachievement of the joint production goal equal to 1.5 units, while production goal of 7 units for product B has been fully achieved. There is an underachievement of the production goal for product A of 3.5 units. What are the application area of goal program? Everyone is worried where it is applied. The goal programming area can be applied to almost unlimited managerial decision areas. Some common areas are in marketing, media planning, and product mix decisions. Production to aggregate, production, planning, and scheduling. Academics, assigning faculty, teaching schedule, university, and admission planning. In HRD, it is related to manpower planning. And in public system, it is related to its application is in transportation system, medical care planning. The next part is integer programming. In LP, each decision variable, slack, and or surplus variables can to take any discrete or fractional value. However, in some certain real-life problems in which the fractional value of the decision variables has no significance. For example, it does not make any sense to say that there are 4.5 men working on a particular project. That means we have to make it specific. The integer solution to the problem can, however, be obtained by rounding off the value of the variables to the nearest integer value. This approach can be easy to terms of economy of effort, time, and the cost that might be required to deliver an integer solution. This solution, however, may not satisfy all the given constraints. Secondly, the value of the objective function so obtained may not be optimum value. All such difficulties can be avoided if the given problem, where an integer solution is required, is solved by integer programming techniques. The area of application of integer programming are capital budgeting, construction scheduling, plant location and size, routing and shipping schedules, etc. Types of integer programming problems. Linear integer programming problems can be classified into three categories. The first one is pure, all integer programming problems in which all decision variables are restricted to integer values. Second one, mixed integer programming problems in which some but not all the decision variables are restricted to integer values. Third one is 0-1 integer programming problem in which all decision variables are restricted to integer values of either 0 or 1. We can see what are the different types of integer programming problems. It is divided, first of all, divided into two problems, that is linear integer programming problems, and the second one is non-linear integer programming problems. They are further divided, and we have different methods of solving this integer programming. And normally we apply cutting plane method because it is applicable both in linear integer programming as well as in non-linear integer programming. The pure integer linear programming model in its standard form can be stated as maximize z equal to c1 x1 plus c2 x2 plus del c and xi, which are again subjected to constraints a1 1 x1 plus a1 2 x2 till which is equal to b1, and similarly we get, and the last one, the most important part is x1 x2 till xn, they are all greater than or equal to 0. As I said, the whole method which is widely used in cutting plane solution, we will understand what this concept is. This method is based on creating a sequence of linear inequalities called cuts. Such a cut reduces a part of the feasible region of the given linear programming problem, leaving out a feasible region to the integer linear programming problem. The hyperplane boundary of a cut is called the cutting plane. With this, we will be concluding today's session and we will be continuing in the next session.